Good evening all, and welcome to tonight's TI Technology webinar hosted by Texas Instruments Australia. And we're really excited to bring you Mathematical Methods Unit 2 with Frank Moyer and Stephen Crouch. My name is John Bayman and I am your host for this evening. I teach mathematics to Year 7 to 12 students at Lachlan Catholic College in Darwin, where I use TI technology to help students make stronger connections in their understanding of mathematics. I'm very excited to introduce our first panelist this evening, Mr. Frank Moyer. Good evening, Frank.
Good evening.
Frank has a vast experience in teaching mathematics, curriculum development, and to strengthen and deepen students, and I might add, teachers' understanding of various mathematical concepts. So thank you, Frank, for joining us this evening.
Pleasure.
Our other sidekick this evening, the wingman, or the equal as well, is Mr. Stephen Crouch. Good evening, Stephen.
Good evening, John. Good evening, Frank. Good evening, everyone.
I could have done a better intro than that, shouldn't I? I was going to call you Robin, but that was a bit of an insult. So I was trying to think of an equal and it just failed abysmally, so I do apologise. So Stephen is a talented and passionate mathematician. I know he relishes the challenge of teaching specialist mathematics to senior students. He's always striving to support every child to understand various challenging concepts. And his teaching is supported by his in-depth understanding of the course and by his use of TI technology, which he's going to share with us this evening. So, Stephen, thank you for joining us as well.
Thank you.
On that note, let's pass over to somebody who's going to actually explain some very cool stuff this evening. I'm excited about hearing from him, and that's Mr. Stephen Crouch. Over to you, Stephen.
Thank you, John. All right.
I hear you're busy at the moment doing reports, so other teachers around the country and the world will be sympathizing with you this evening, Stephen.
Oh, that's exactly right. But I must say this will be very enjoyable, so I'm looking forward to it.
Okay, thank you. I can see your screen. It's all yours.
Excellent. Thank you very much. All right, everyone. So thank you for tuning in this evening. Frank and I have a lot of stuff for Maths Methods Unit 2 ready for you this evening. Frank will be going through some algebra and probability topics, whereas I'm going to be focusing more on the trigonometry and calculus sections. So in trigonometry, I've got a few little demonstrations for you. I've got symmetry in the unit circle, the graphs of sine and cos from the unit circle, a dynamic visualization, and then finally some modeling. So, you know, as teachers, we sometimes struggle with the concept of modeling and explaining that well to the students. So with the file that I've got here, it should help with that just a little bit at least. And then we move on to calculus, where we can talk back to what the derivative means, f dash of x, and then finally go to differentiation by first principles, again, a quite poorly misunderstood topic. So just as a quick overview of what each thing is going to be, I'm going to move through to each page and show you pretty much what's going to happen. So when we do symmetry in the unit circle, we might have a look at a diagram such as this, or at least draw something similar on the board. Now, while diagrams like this are quite helpful, I think as a student, it would make more sense to have a dynamic representation of these concepts, and I'll show you a few files which go through something similar to this. So, as you can see, I've got 12 unit circles over here, each regarding multiple angles as you go from quadrant to quadrant. And then on the right-hand side, it's a sort of a fill in the blanks for the students as they go through this particular concept. After that, I'm going to look at how do we get the graph of sine x, and we use the unit circle for that. So I'll have a unit circle on the left-hand side. We'll increase the angle using the slider here. And basically, eventually, this graph here will get generated. Then we move on to cos graph, something pretty similar. Then we'll go to modeling using trigonometric functions, which is the heights of tides. And then I'll show you as well how to actually get a few things using conditional statements inside your calculator screen. Pretty cool stuff. And then moving over to calculus, I've got the parabola y equals x squared. I'll have this big red dot here. I'll grab it and I'll start moving it left and right. And as I grab it and move it, this gradient will be grabbed from here and plotted on this graph on the right-hand side. So we put that up on the projector or even give it to students on their handhelds. they'll be able to physically see what the derivative is doing. And finally, to finish off, the good old topic of differentiation by first principles. So again, I have y equals x squared, the blue graph there, and the black dot is where our point x is. Then I'll have a brown dot there, which is x plus h, and I'm going to start grabbing points and moving it around and seeing what that red gradient is in comparison with the green gradient. And I'll also talk about how we can basically inform our students as to the mathematics behind all this. Okay, so without further ado, I'm going to get started on some symmetry. So the first thing that we do in trigonometry really is we look at the unit circle and we look at these main angles of 30, 45, and 60. And then we sort of go to the radian equivalents, which for 60 was pi on 3, 45 was pi on 4, and 30 was pi on 6. And of course, the main idea really behind this whole thing is these coordinates there. And we go ahead and explain that the x value of the coordinate is the value of cos of the angle, and the y value of the coordinate is the sine value of the angle. So we can do that quite easily, and usually at that point, students understand what's going on. And then where the confusion usually arises is when you move to the second, third, and fourth quadrants. So with the diagram such as this, what I've got is I've got the angle 150, as you can see at the bottom, which is equivalent to 5 pi on 6 radians. What I've got here is also the coordinate on the left-hand side of this point here. What we can clearly see is that the x value is negative root 3 on 2, which is the negative of the x value of the pi on 6 angle. And then you look at the y value, which is half, and you can see it's the exact same as the y value of pi on 6. So from there, using that one data point, we can basically say that sine of 5 pi on 6 is equal to sine of pi on 6. And then sometimes you might wonder, okay, well, how can we show that more generally, or even do it with more angles? So I've got the slider at the bottom. You can keep pressing that to go to different angles, at least our main ones of pi on 6, pi on 4, and pi on 3. And as you go through that, the coordinates on the top corner over there are basically showing that the sine value remains the same when you're on the second quadrant, and the cos value is just the negative of what it was in the first quadrant. So that takes you through the second quadrant. Then you can go to the third quadrant, but not only are we looking at the third quadrant, we can also look at the second quadrant. And as you move through the angles, you can see the relationships between all these coordinates. Of course, this can breed some very rich discussion with the students regarding how the symmetry works in the unit circle, how we can take an x value from here and transform it to an x value there, and the transformations and the symmetry that's going on behind the scenes. So of course you can do all that, and then you can bring the fourth quadrant in as well. And here we go.
Stephen,
here's the fourth quadrant. Yes?
Somebody just asked, they're actually teaching this at the moment, and they were saying that they would love to use this with their students. And obviously I presume this will be available for people both on demand and live to actually get after this recording this evening?
That's correct, yes. Every single file that I go through, which is all these ones at the bottom, I'm going to make available via upload on the on-demand section of the website. So as soon as this webinar is over, all these files will reset back to their default states, and we'll upload them, and then anyone can download them for use later on.
Fantastic! You've made some teacher this week very happy. Thank you.
That's great to hear. Thank you. So that's with the fourth quadrant there. As you can see, we can change up the angles, and you get this nice bow tie looking thing. So of course you can talk to the students about how this is really cool from a mathematical perspective. But of course, when they go to their school formals, they can make bow ties using trigonometric functions. How cool is that? So that's pretty much that for symmetry. I've also got other files like this where it's not just limited to pi on 6, pi on 4, and pi on 3. Rather, it's a more general sort of file where I've just got a random, a basic unit circle over here, and all I've done is create segments between the origin and points on the unit circle, and then reflected these points over to the left-hand side. And then as you grab this point, the reflection, of course, follows along with it. And this, again, conclusively proves that sine of pi minus theta, which is this one here, is equal to sine of theta. If you do want to bring angles into it, you can actually modify this the diagram quite easily. You can go to Menu, Geometry, Measurement, and Directed Angle. And from there, you can take the right-hand side, then the center, then this side, press Escape. And now what we've got is we've got a directed angle from the x-axis to the top there. And as you move, of course, you can see the radians increase. But the really cool thing is the radians actually increase past the y-axis and all the way to the bottom as well. So you can actually start talking about this file without that angle there and just show it as a general case about what happens when you move this point around. And then, of course, you can breed more discussion regarding the directed angle over there. Likewise, we can do the same thing with cos. You can take this point in the first quadrant, start moving it around, and as you can see, the equivalent point in the fourth quadrant basically keeps the same x value as you move up and down. When you go to tan is a bit more complicated. We've got our tangent line on the right-hand side, but as you move this line here, we can then go to the second quadrant, and as you can see, the point there on the red line is moving according to this one as well. And you can then, of course, bring discussion about symmetry for the tan function as well. So finally, what I'd like to move on to is something a bit related to symmetry, but not exactly the same thing. What I've got here is a file that talks about what it means when you're actually solving a trigonometric equation. So on this diagram, we're going to be looking at what it means to solve an equation of sine x equals something. So for example, have a look at the top row here. We've got y equals 0.0. And I'm going to grab this gray point and move it so that y equals 0.5. And as soon as I've got y equals 0.5, I've got this coordinate x comma y, which I've called a gray one. And then I've got a green line that's traveling towards the y-axis. And you can quite clearly see that the y value of that green point and the y value of that gray point are both 0.5. And then what is shown is that the angle that produced that point there is 30 degrees. So what that means is if you're solving sine of x equals, or sine of theta rather, equals 0.5, then one of the angles that produces that particular value of sine is 30 degrees. And then, of course, you can bring in more discussion about, well, are there other possible angles that get you the same value? And then you can say, well, what about the second quadrant? There should be a point on the left-hand side here. Correct. So a point from the left-hand side that goes and gets the exact same y value of 0.5, and there we go, we get 150. So of course you can then tie that discussion back to what we did in symmetry and how an angle that is in the second quadrant gives us the same y value as the equivalent angle in the first quadrant. So you can get 0.5, and then you can talk about things like getting negative 0.5, etc., and you get 210, or you can go all the way to 330. Where are we? There we go, there's 330, and 0.5 is, or there we go, 330 and negative 0.5. Sometimes it's a bit, it can be a bit finicky when you're at the front of the class and, you know, tensions are running high and you're trying to get everything right. So sometimes, one time I used it and it completely stuffed up and I looked like a fool in front of my students, but it did work out in the end finally. So hopefully when you use these files, it shouldn't give you too much of an issue. So that is sine x, solving sine x equals a specific value. And likewise, I've got a very similar file for cos of x. So there's our gray point. Again, if I start grabbing the gray point, if I go to something called x equals 0.5, again, you can see when x equals 0.5, we get an angle of 60 degrees. So of course, solving the equation cos theta equals 0.5, one of the angles we get is 60 degrees. And then again, you can say, well, what happens if you go to the fourth quadrant? And then you end up with the value of 0.5 as well for cos. We're almost there, yep. And you end up with 300 degrees like that. And then you can also talk about getting cos equals negative, negative there, etc., etc. You can have quite a bit of fun with these files really if you sit down and play with them a bit. But of course, don't get too carried away. Okay, so that's the end of the symmetry component there. What I'd like to quickly move on to now is showing how the graphs of sine and cos get generated. Now, this is an area, again, that a lot of teachers and students face difficulty with. They look at a graph of sine of x and they wonder, well, how do we get that sinusoidal periodic nature? How can we get that from a circle? What's going on? So if you put a file like this on the projector, and then you just take the slider and start increasing. So we've got the slider that goes up in increments of pi on 12. You can just increase it one by one. And what you can see is that as the angle increases, you end up with different values for the graph of sine theta. Okay, it looks like something's going on with the file over here. I'll have it fixed for later on. But basically, when you have this file over here and you look at the circle, what happens is that each height over here gets transferred over to the x value. So for example, at pi on, let's say, pi on 3, when x equals pi on 3, you end up with a height or a sine value of root 3 on 2. So what that will do, this red line will transfer over to where pi on 3 is and create a y value there. And as you increase the file, at pi on 2, of course, it'll get to 1, and then starts decreasing again all the way till pi, and then you'll generate the rest of the file that way. So you can show that with sine of x. Likewise, with cos of x, it's something similar that happens. However, with cos, it's a bit trickier because the x value of our cos graph, or the x value of the unit circle, becomes effectively a y value on the cos graph. So this one will require a bit more explanation and a bit more going through, but I reckon just a couple of revolutions around that unit circle and everything will be pretty sweet. Okay, so another I guess, file that shows this unit circle is something pretty similar over here. So again, this time I've got an animation where I've got the angles increasing on the unit circle, and as you can see, the angles as they are increasing, this red line here, as it's becoming larger, smaller, etc., is basically copying and pasting itself onto the graph, and you end up with the entire sine graph over a domain of 0 to 2 pi. I think this is really cool in the sense that if you press that play button, you can literally see the relationship between the height of this point on the unit circle and the height of these blue points on our Cartesian axes. Likewise, if you go to a cos graph, similar deal. You've got the value, this x value of this red line here, which transforms to the height or the y value on the Cartesian plane here. So again, I can start the animation. As the angle increases, we've got our x value decreasing, and you can see that quite clearly on the graph as well. So I'll let that rotation complete fully. But yeah, in terms of like being in class, I think showing something like this is quite good because you can't really have a textbook showing something as good as this in terms of just the dynamic capabilities of what's happening with the TI-Nspire. So of course, once you get your hands on these files, feel free to play around with it. You can annotate things if you'd like. You can do quite a lot of things with it. And then finally, really, I think this is a really cool thing that we can do. You can actually identify what's happening with sine and cos together. So this is really more for the advanced students. If they can have a look at the base and height of this triangle simultaneously, they can kind of see what's happening with the graphs of sine and cos simultaneously. And furthermore, you can then discuss things like, well, what's happening when sine and cos are equal? What's happening on the unit circle? And then they can talk about, well, if it's an angle of 45 degrees or even 225, yep, 45 or 225 degrees, then you can see how the base and the height of those triangles are the same, and that's why sine and cos are intersecting at the same points there. Okay, so I think that does it for the trig component. I'm going to quickly go to application, and what I'm trying to show over here is basically we have these typical questions about the heights of tides. So you have the height of the tide in a harbor, at the end of a pier, etc. These sort of situations. And a sample example is we have the height being 6 plus 2 sine pi t on 6. We can then talk about questions like, well, what's the period of this from the equation? So 2 pi divided by pi on 6, that's equal to 12, etc. So in one day, you kind of get 2 full cycles or 2 full periods. The amplitude is 2, the max is 6 plus 2, which is 8, the min is 6 minus 2, which is 4. So of course, those are the sort of basic fundamental questions that you can start off with. And then you can start getting questions such as, well, a boat, for example, can only enter or exit the harbor or pier or whatever it happens to be when the height of the water is, when the height or depth of this tide is strictly above 5 meters. So what I've done here is I've drawn a dashed line at h equals 5. Of course, it's not an asymptote, it's more just a reference point. And at the same time, I've also got a third graph here. So just showing you how I've done this, I've basically got F1, which is a sine graph. Of course, I've used x because that's what the CAS takes in. And then our second graph is just h equals 5, nothing too crazy there. But the third graph is, this is something really cool with conditioning you can do. What I've said is I've said that the third graph is just the first graph. So whatever it happens to be, the first graph, I want to graph it, but only on the sections where the first graph's y value is less than or equal to 5. So what's happened here is that second graph only sketches the parts of the first graph that are strictly on or below the line y equals 5. So that's where the black graph comes from. And then what I've done is press another slider there, and again I've shown the actual times at which the height or depth is equal to 5, and then we can talk about, okay, well, what's happening, what times is the depth or height of the tide above 5, and therefore we can figure out the percentage of the day in which a boat can enter and exit the harbor, and all those sorts of advanced questions that can come along. So there's another capability of the TI-Nspire that can really help bring some of these questions to life. So I'll finish off the trigonometric section there. I'll quickly show you 2 parts because I'm very about the time over here. It's going pretty quickly. Hopefully you're all having fun looking at this stuff and can imagine ways that you can use it in your own classrooms. So in calculus, of course, the main thing that we look at is taking a graph such as f1x equals x squared, and then taking almost every single point there, a collection of points, finding the gradient of the tangent to the graph at that point, and then plotting that gradient on a new graph. So here I've chosen a random point, 1.35 and 1.83. And what's basically happening in the background is the calculator is capturing these x values, which is 1.35. It's also capturing the gradient of that green line. And what it's doing is it's plotting the x value of that red point versus the gradient of the tangent at that point as well. And as I grab this point and start slowly moving it, there we go, what you can see is on the right-hand side, we are basically generating a new function's y values. So as you slowly move throughout, what you can see is we've got a bunch of positive values. And then if you look carefully at as we approach the turning point, at the turning point, suddenly we have a gradient of 0, and we also have an x value of 0. That gives us the 0.00 on this graph. I can drag that point, now take it to the left-hand side, and as you can see, we're getting more and more negative gradients there. So negative x value and negative gradients. And then, of course, you can see a little gap over there. So I've skipped a few points. Let's just go and fill that in. There we go. So you can play with this file pretty much as you like. And I think in the way I've made it, you can actually even go and change this x squared to an x cubed, for example, if you'd like, and then repeat the same sort of procedure. So in page 1.2, as you can see, I've got xplot and gplot. And what's happening is I'm taking all these x values that I've generated from this red point and plotting it against the gradient of the tangent on that. So there's a data capture feature that is really good for this. In future webinars, I'll be going through how data capture works and how to do it. But for now, it's just a spreadsheet with a bunch of values in it. And on the right-hand side, I've got a scatter plot of all these values plotted with each other. So to finish off in the last 2 minutes, I'm going to look at first principles. So after we look at what the meaning of a derivative is, sometimes we like to show the first principles method, which is that limit as h approaches 0 of f of x plus h minus f of x over x plus h minus x. Again, it's a pretty lifeless formula, but you can certainly bring that to life with an interactivity such as this. So again, I've got y equals x squared, and on here, I've got the black point there. Now you can actually make that black point anywhere you want along this parabola. So for example, let's just make it at x equals 1. So at x equals 1, we know that the gradient of x squared at x equals 1 is equal to 2. So we know that the gradient is equal to 2 at that point because that's the gradient of the tangent. Well, when you're looking at the gradient of the secant, which is this red dashed line, what we can do is we can say, well, if you move your black point to the right by h units and then go to this brown point, well, what happens as you grab the brown point and move it closer and closer and closer to this black point here? What you can see is that this red number, which is representing the gradient of the secant, is slowly approaching, limiting to the value of 2. And as you get closer and closer, you basically end up with exactly 2 when the 2 points are coincident with each other. So of course, you can do this and then move the point to another value as you like. You can go to x equals something to get y equals, get the gradient equals to 3. Almost there, all right. So we're almost there. So at x equals 1.5, of course, you get a gradient of exactly 3. And then you can grab this brown point and move it left and right and show the same thing as well. So of course, it's not restricted to a single point. It's quite a dynamic representation, and you can do really cool things with it. As before, you can change that x squared to whatever you like. So you can talk about a sine graph, log graph, exponential, trigonometric, whatever suits your fancy. You can change it, and this file should work along with it as well. So I can change that to a cubic graph, and it does the exact same thing. I can move the point around, and it does the same thing. Pretty cool stuff. Okay, I think I'll put an end to it there. I think I was having a bit too much fun. I can't steal it away from Frank. So back over to you, John. Thanks so much for listening, everyone.
That's great, Stephen. And I think that a really nice point that you've made there is that you take something that's fairly dry, and by making it interactive with the TI-Nspire technology, it brings it to life. And I think that's a really nice comment you made. And like you said, with using, say, a smart board or an interactive whiteboard, getting the kids to come out the front and actually touch those points and move them and see it actually happening is fantastic. So thanks for sharing that tonight, but also thanks for sharing those documents for other teachers to use.
You're welcome. Thank you.
Thanks. Okay, Frank, we can see your screen. It's all over to you. Thank you. Good luck.
Thank you, John, and good evening and welcome, everyone. For my part, I'll be, first of all, talking about probability and statistics. And first activity, I'm going to concentrate on the last dot point in the VCE study design, which is on combinations and the concept of selection and computation of NCR. So I'm going to have a look at dynamic computation of NCR using a slider in a notes page. So we can calculate NCR in a calculator page. So if we go menu and probability and combinations, except I'm not in the right spot, then I could, for example, have 4, 2, and it works out 4C2. But if I want to repeat that, then I have to edit. I have to copy and paste it and then edit. Whereas you can do it interactively and dynamically if you use a notes page. Now, to save time, I've already put a slider in the notes page, and I've called the variable K. And if you want to add a slider to a notes page, it's just menu and insert, and you'll see that number 5 is slider. And the other thing, to carry out the dynamic computation, it needs to happen in a maths box. which you can go through the Insert menu or Control-M as the shortcut. Okay, so when you're in the Maths box, if you go to Menu and number 6, Calculations, you'll see that you've got the same menu as in the calculator application. So we can go to Probability and Combinations, and we get our NCR there. But the difference is that because I've got a slider with K, I can now have K, comma 2, for example, and 6C2 is 15. But if I change the value of K on the slider, then the value will be, the result will change dynamically. Now, I could generalize that by having an R there, and I get an expression in terms of R. But I could then assign, using a sequence command, I can assign all the values of R from R equals 0 through to R equals K. So to get a sequence command, I'll go through the catalog. So I'll hit the catalog, the big book, and sequence, so I'll press S. And the reason for going through the catalog is that down the bottom here, you can see the syntax, which is the expression, the variable, the low value, the high value, and the step size, with the step size of 1 being the default. So sequence, and I'll get rid of that bracket there. So that's the expression, comma, the variable is R, and I want to go from 0 through to whatever my value of K is. And I get, because K is 5, 5C0, 5C1, 5C2, and so on. And if I change the value of K, then obviously the all of those values change. But I could generalize this further by changing that K in there to an N. And I get an expression in terms of N. But once again, I can get a sequence command and assign values of N from N equals 0 through to N equals K. So again, sequence, get rid of that bracket. Okay, so that whole sequence command is my expression. The variable this time is N, and I want to go from 0 to K. And this time I get all of those combinations. So in fact, I get Pascal's triangle. And that's actually quite a neat form of Pascal's triangle. So for example, looking at the triangular numbers, if we have a look at the third column, it's quite clear, 1, 3, 6, 10, and so on. The sum of any two triangular numbers gives a square number. It's quite an easy way also of seeing that if I find the sums diagonally, 1, 0, and 1 is 1, so 1, 1, 1 and 1 is 2, 2 and 1 is 3, and so on, I get the Fibonacci numbers. So that's actually then quite useful, quite a useful representation of Pascal's triangle. Now, even though
Frank,
Pascal's triangle...
I was thinking as well, sometimes as well, although it's called Pascal's triangle and we normally see it as a triangle, seeing it that way, actually it's leveled up, gets you to see more patterns as well sometimes. It may make it easier for certain students to see it compared to actually having it in the traditional Pascal's triangle method.
Absolutely. I think that in fact a lot of those patterns are obscured by the fact that you've got the isosceles triangle pattern. So that's quite cool. So it just illustrates the use of the dynamic features of Nspire if you use a notes page versus rather than just a calculator page. Okay, now the other probability activity I want to talk about is one that I wrote for the Senior Curriculum Inspirations. So if you go to the TI Australia website, which is just education.ti.com/Australia, under the teacher section there's a section called Senior Curriculum Inspirations, and in the Victorian section, although this is not unique to Victoria because it's to do with sampling with and without replacement, there's this activity which aims to explore the results obtained from random sampling and show how samples vary from one sample to the next, estimate probabilities from the results of simulations, compare probabilities for selection made with replacement and selection made without replacement, and lastly, compare experimental and theoretical probability. Now, this activity, if you go to the website, has got a student and teacher worksheets so that it's all ready to go. So you get the TI-Nspire file and the teacher worksheet, student worksheet and teacher notes. Okay, so the problem involves having an urn with 5 blue, 3 green and 2 red marbles, and we're making selections with and without replacement and making a comparison. So the list, which I've called urn, contains 4 Bs representing the, 5 Bs representing the 5 blue marbles, 3 Gs representing the 3 greens, and 2 Rs representing the reds. And I've put this page in so that teachers can see how it was created. So I've used the random sample feature. Now, if you go to Catalogue, and we'll go to ARF and down to random, you see that there's random, random binomial, random integer, random matrix, random normal, polynomial, and random sample. And from random sample, you can choose anything from a list. Now, it doesn't have to be numerical elements in the list. They can be symbols, they can be letters, or whatever. And the syntax is list. You can see down the bottom, list, the number of trials. The default is selection with replacement. However, if you write (1), it's selection without replacement. So that's that's how the sample is drawn. So if I draw a sample using the slider, we see up the top here we've got 2 blues and a red, and the other sample, which is the one without replacement, a green, a red, and a blue. And I've used a count if statement further down. So count if in our random selection the letter B appears. So you can see down here the 2 in the brackets, which means that there are 2 in the first list, 2 blues in the first list, and only 1 blue in the other list. Okay, and those results are shown, are displayed in dot plots. So the blue is with replacement, and the red, the top one is with replacement, the bottom one without replacement. And as I draw more samples, it populates the list. Now I'm capturing these values not using data capture, but with a small program. There's a statement called an augment statement in that you can use in a program, and it captures into a list. Okay, and I've got the same results there, but in a histogram. And you can just hit reset and start again. So that's basically the TNS file, and the results will then appear on a spreadsheet. That's just the program used to do the capture. It's probably not a very elegant program because I'm not a programmer, but it works. Okay, and in the next page, the next problem, the same thing, except this time we're simulating 1,000 trials. Now, it's probably not a good idea to give students this on the handheld. The first one with 100 trials is fine. 1,000 trials, it might slow their handheld a bit too much, so it's probably better to demonstrate using a projector. And once again, you simulate 1,000 samples at a time, and the results appear with replacement, without replacement, and then the results on page 2.3. Okay, so because I hit that 1,000 trials 6 times, I've now got a total of 6,000 trials, and we can see the proportion. So it's about 1.3 with replacement for 0 and for 3 blues, and about 0.38 for 1 or 2 blues. And we can see that the proportions are different with and without replacement. Okay, I'm not going to say too much more about that because you can have a look at that file yourself. All right, so the other thing I want to have a look at under the algebra area of study in the VCE study design, the last dot point is talks about numerical approximation of roots of cubic polynomial functions using Newton's method. So what is Newton's method? So this is a root-finding algorithm used to calculate increasingly better approximations to the root of the equation f of x equals 0 with each successive iteration. So why is this on the Victorian syllabus? Well, I suspect the reason is that students should have an understanding of algebraic, graphical and numerical methods of solving equations, and for them to realise that many equations cannot be solved by factorising and using the null factor law. In fact, most of the equations that we would come across in engineering, once we go beyond quadratics, cannot be solved analytically, and a numerical method needs to be used. So the important thing is not the answer. The technology will give us the answer by magic. It's understanding the process. So back in page 1.3, I had a description of how it works, but I'll demonstrate it graphically. So I've got the graph of a function that's got a root over here somewhere, and I take a first guess, which at x0. So I guess that the root is approximately x0. So what I then do is approximate the graph of the function at x0 by its tangent. So the tangent will intersect the x-axis at a point x1. Now, if my initial guess x0 was a reasonable guess, then x1 should be fairly close to the true value of the square root. Sorry, of the root. For the next iteration, I then take the value of x1 and approximate the graph to the tangent at the point x1. And that tangent now intersects at another point x2. Now, provided that my initial value was well chosen and something hasn't gone wrong, and as we'll see, sometimes things can go wrong. If nothing has gone wrong, then the next approximation should be even better. So for the next iteration, I take the value of x2 and approximate the graph with the tangent at x2. And this time, certainly on this scale, you can hardly tell the difference. So that's how it works. All right, so it's also a formula. So where does the formula come from? So for the nth iteration, the equation of the tangent at xn, f of xn, is we just need to apply y minus y1 equals mx minus x1, where instead of for y1 I'm using f of xn, and my gradient, is f dashed of xn. Now the tangent will intersect the x-axis at a point xn plus 1, 0. If I substitute those values into the equation, so I replace the y with 0 and the x with xn plus 1, then substitute those in, I get the last equation there, and then I just rearrange the equation, and I get that the next iteration, xn plus 1, is equal to xn minus f of xn over f dashed of xn. Now, a spreadsheet is quite a good way of seeing that happen recursively, and I think that because it's the procedure, not the answer, that matters, I think that students should need to see each successive iteration. So in the notes page, to save time, I've already entered the f of x and my initial guess at 2, and I've also got the derivative. So in the spreadsheet, I'll call this column xn. That's going to be my xnth value. And this one, I'm going to substitute xn into the function. I'll call that fxn. And this one I'll call the derivative of f of xn. Right, so my initial value of xn is the one that was x0, so I'll grab it from here, x0, and now f of xn equals, so it's going to be f of whatever I have in cell A1. And there's a reason why I'm entering it this way, because as I fill down, it should update the cell reference. And this one is the derivative at that value. So that's, I call that df of whatever I have in A1. Right, now for my next value, it's going to be whatever I had in A1. If you remember the formula, it was xn, which I've got in A1, minus f of xn, so which I've got in cell B1, divided by the derivative, so which I've got in C1. Okay, now I'll go to this cell. Now to multi-select on the handheld, just hold down the Shift key and then use the arrow so you can multi-select. Then to fill down, a number of ways of doing it on the handheld. One quick way is just to get the context menu, so Control menu, and number 4 is fill, and just press the down button. Now I'm only going to fill down to there for the minute. As we saw here, as you go down from one cell to the next, because I've used a relative cell reference, the A1 is updated to A2, and the same in this one here. The A1 here is updated to A2. Right, I'll hold the Shift key down and select all of those and start filling down. So Control menu, fill. Okay, I'll get up to 10 iterations. Let's see what happened. My first guess was not very good. I mean, I started at -24. Now, the y-coordinate of a root has to be 0, so -24 is not even close. Then it gets even worse, 59.9. But this is the beauty of Newton's method, when it works really well. It's very fast, so it very quickly converges. We can see that the y-coordinate of the approximation to the root converges to 0 very quickly, and the x value converges to 3.16228 very quickly as well. And that okay, so that's a way of showing the recursion. If you want to emphasize the formula, another way of doing it is to do the recursion in a calculator application. So to save a bit of time, I've already set this up. So I've got my value x0, which was 2. I'll just go back and show something else, just to illustrate that sometimes things can go terribly wrong. I'll go and change my x0 to -2. All right, and I'll go to my spreadsheet. No, that's not what I wanted to show. Okay. Right, yeah. Okay, it hasn't worked terribly well, and as we can see, there are for particular, if your starting point is not well chosen, then things can go horribly wrong, as they have in this case. So it hasn't worked well. All right, back to this one. I've got the formula given that x equals the previous answer. Now, once again, I can select all of that and Control-C to copy it. Something always goes wrong when you do these things live. Okay, try it again. No, to try with ones you prepared earlier. Not sure what I've done wrong. But anyway, if you using that formula, you should be able to then successively show the recursion in that application.
Frank?
Okay. Yep.
Is it because you're using a stationary point as the initial guess? Is that affecting it?
Oh, that's right. Yeah, yeah. Sorry, it's because it's because of my initial. Yeah, that's why. Yeah. So, that's why it didn't work in that particular case. Okay. All right. So non-convergence in this particular case, you can see that if you end up at a stationary point, this is why it wasn't working. If either because of your initial guess or because somewhere along the line you end up at a stationary point, then the whole thing falls over, which is why that wasn't working. Okay. The other reason can be just because you end up in a cycle. So you can end up at a point where they just it just keeps going round and round in circles, and you just can't get a solution. Okay, I'll just go back since I've only got about a minute left. I'll go back and change this to something that will work, such as -1.8. And we see that the spreadsheet now works because I actually had a value that made sense, and hopefully this one works as well. No, okay, all right. Anyway, it was working perfectly well this morning when I tried it. And there is another file that I've got on transformations that I'm not going to go over because it's one that you can have a play with yourself. So by all means, feel free to download the one on transformations and have a play with that. It's similar to something that Stephen was doing where you can use these controls to manipulate a point. Okay, and my time's over, so thank you very much for listening.
Thanks, Frank. I think it's always the way. Your document works fine, and then you try and show off a little bit to other people to just show a few bit extras, and then obviously it's got a glitch in it. So obviously if we started that program again, it would work fine. So thanks for sharing that with us. And like I said, obviously you're keeping it off that stationary point. All right, so we'll begin wrapping things up now. And if you do have any last-minute questions, please try and get those asked. I know that Stephen and Frank are watching the chat and the Q&A window. I know they're in endeavour to answer them, or they'll add them to planning of future webinars. As you leave the webinar tonight, a brief survey will automatically appear here in your browser, and your feedback does guide us as we plan future online events. We do listen to your feedback, and so we hope you share your thoughts in a post-webinar survey. Your most important certificate of attendance will be emailed to you in the next 48 hours, along with the on-demand and YouTube versions of the recording, as well as the relevant documents that both Frank and Stephen shared this evening. And if you would like, after you leave tonight, any post-webinar follow-up, please feel free to phone or email TI. I know they'd love to hear from you and support you in any way they can to make your teaching in the classroom with TI technology even better. And sadly, that brings us to the end of tonight's webinar. Thank you very much, Stephen and Frank, for everything you shared with us tonight.
Thank you.
Thank you.
I know I've certainly learned a few things, and I know that from the feedback from the participants they have as well, and they've really appreciated what you've said. So thank you very much, and thanks very much for sharing those documents. And equally, thank you, everyone, for joining us this evening or watching it on demand. I hope you found it useful. I hope you share it with your friends, and all the very best in your teaching in your classroom. Thank you very much for watching, and we'll speak to you and see you again soon. Thank you, and good night.
Good night, everyone.
Good night, everyone.